So we have a lot of information about these trigonometric functions. We've taken a look at the graphs of them. We've taken a look at properties of them. We've built definitions about these trig functions. What we're going to talk about today is the inverse of these trigonometric functions. So because for some of us it's been a while since we've done some algebra stuff and we've talked about inverse functions, I want to just start off with a quick review of inverse functions. It's going to be real quick. I'm not going to go too far into things. Hopefully it'll just be a nice reminder of some of the properties. If you need some more in-depth reminders, take a look online in the text. There's some kind of hints along the way and things like that. Hopefully that'll be pretty helpful. Once we have that review of inverse functions in general, we're going to take a look at the 6 trigonometric functions and their inverses. We'll figure out where they are in a calculator so that we can use them to do some things. And then we're going to end up with doing some composition of functions with inverses, which maybe sounds a bit familiar from algebra classes. There's some good properties that we'll be able to use. Anyways, here's our quick recap of everything we should already know about functions and inverses. So I've got 4 bullet points, which seems like, well, I guess there's 5 if you count this one, which seems like not that much. But within this, there's a lot of conceptual stuff. So the main key is that an inverse function switches the inputs and outputs. Sometimes we think of it as it like goes backwards through a function. So it takes the output and it matches it up with an input instead. So the example that I was given in algebra class is, let's say that a function takes a group of people and matches them up to their, their student ID number. What the inverse function would do is it would take the student ID number and it would tell us which student that is. So it just goes backwards through there. We're putting the opposite thing into the function and getting the opposite thing out of the function. So that's why we've got this notation. X equals f of y is the same thing as y equals f inverse of x. This -1 exponent is not really an exponent. This means inverse. That's a bit of a confusing notation on functions, but when you have that -1 on a function, it means inverse. A function composed with its inverse undoes itself. Since they kind of go backwards through each other, f of f inverse of x is just going to spit out x. You can think about it this way. If these are x values and we've got some point here, and these are our y values and we've got some point here, our function connects things this way, and our inverse function goes backwards. So if you compose these things, you end up just kind of going around in a circle, and you end up with what you started with. Same thing as if we compose it in the opposite way. So it doesn't really matter which way we compose things, you're going to end up with just whatever the input was. For a function to have an inverse, it needs to be 1-to-1, pass the horizontal line test. What this means is that not only does every input have to have only one output, but every output can only come from one input. If we go back to that student example with the student ID numbers and names, that example doesn't work very well if we match up students with their age. Because if we try and go backwards and we match age up with students, we might get a whole bunch of students that are the same age. And it's pretty likely to be the case if we're in a college class. So we need to have this 1-to-1 behavior, pass the horizontal line test. If it's not 1-to-1, it has like an inverse, but that inverse isn't a function because it has multiple things that it's going to spit out. And then the graphs of these functions are reflected across the diagonal line, y equals x. This is a bad drawing, but whatever. Maybe I'll grab my straight line thing. So if we have a set of axes like this, then our inverses are reflected this way. So maybe we have one function. Oops, I want to get rid of my straight line now. Maybe we have one function that looks like that, and then the inverse function is going to be reflected along here. So it's going to look like that. Oops. There. Not perfect, but oh well. Cool. Because of this, we can pick a point on here. And if this is a point A comma B, then the reflected point over here is going to be B comma A, which makes sense because, again, this inverse function just switches the inputs and outputs, so it switches the coordinates around. So hopefully that's helpful just to kind of do a quick recap of these things. So let's get back to some trig stuff. Let's talk about inverse functions. So inverse trigonometric functions. They're going to be giving us angles. Our normal trig functions are things like f of, oops, let me fix this, sorry. F of theta, which is sine theta, for instance, where our input is an angle, and we get out a ratio of sides of a triangle, or maybe some coordinate on the unit circle, or something like that. With the inverse function, we're going to be spitting out angles, and we're going to be putting in a ratio of side lengths or coordinates on a unit circle or something like that. If we think about the graphs of our trig functions, like here's sine or cosine depending on where I put my axes, you'll notice pretty easily that this is clearly not 1-to-1. It does not pass the horizontal line test. If you draw a horizontal line through here, we got a whole bunch of spots where we cross this graph. So that's going to be a problem for us. We're going to have to do this little trick where we restrict the domain of our sine function to force it to be 1-to-1. There's a really easy example for this. We could say y equals x squared and y equals square root of x are kind of inverses of each other. The problem is that x squared is not 1-to-1. For instance, 3 squared is 9, but negative 3 squared is also 9. When we look at the square root, we only give the positive answers. So if you look at the square root of 9, that's 3, not negative 3. So we make a little domain restriction on here that says the square root only spits out positive values. So you might think, well, that's not really a restriction on the domain because it's a restriction on the outputs. What we're doing is we're restricting the domain of the x squared function then. So we take this parabola and we say we're really only looking at this portion of it, not this half. And so we reflect this one, and we end up with this nice square root graph. And so we don't have the negative version. So we're going to do the same kind of thing here. Hopefully you've seen a little bit about that in algebra classes. So let's start with our graph of sine of x. I've just plotted this between negative pi and pi so we can see one kind of period of this thing. And so clearly, if we kept going, this thing is not 1-to-1. So what we're going to do is we're going to restrict just between negative pi over 2 and pi over 2. I've got that in blue. Hopefully you can see that. That way, if we try and draw some horizontal lines through here, sure, it goes through the whole green graph more than once, but it's only going to hit the blue graph one time. So if we restrict it, we've gotten all of the values in y from -1 up to 1, and we just have to use a portion of our x values. So we're looking at from negative pi over 2 to pi over 2. So this is the piece of the sine function that we're going to reflect. So let's go ahead and reflect this thing. Let's see if I can draw a nice line. Perfect. Looks something like that. So when we reflect it, that's what we get. Hopefully you can see that that's a nice reflection over that line. Well, it's not perfect. My line is kind of bad, but oh well. So that line then gives us this nice inverse function in red. So this is the graph of our inverse sine function. If we go back, you might notice that this point right here on the end is pi over 2, comma 1. And we've got this point here, negative pi over 2, negative 1. So that means that this point over here is actually going to be 1 comma pi over 2. And this point here is going to be -1 comma negative pi over 2. So that's what we've got. We've got those two ending points. 1 pi over 2, -1, negative pi over 2. You'll notice that the origin, 0, 0, gets reflected to just be itself. So these are the points that we're going to be noticing. Again, you're putting in a ratio of side lengths, you're getting out an angle here. And this only spits out angles between negative pi over 2 and pi over 2 now. So that's something to just keep an eye on. So here's what we've got. Here, quick little summary. If we had x equals sine theta, that's the same thing as saying theta equals sine inverse of x. So now x is that ratio of side lengths that we're putting in. Theta is the angle that we're getting out. Since sine theta was not 1-to-1, we restricted the domain, and we restricted it to this. So that was the domain of the sine function. So that ends up being the range of our inverse function. So our sine inverse only gives us those angles between negative pi over 2 and pi over 2. The domain of our sine inverse function is all the possible ratios of those side lengths or coordinates of the y value on the unit circle. So it goes between negative 1 and 1. Cool. One of the things that we might just draw real quick is to say if we had like a nice unit circle here. My circle's going to be terrible. I already know it. All right, it's not so bad, but oh well. The angles that we're looking at are all the angles in between negative pi over 2 and pi over 2. So that's all the angles down here and up here. So our sine inverse function only spits out these angles, which you can tell then are also values where the y value goes from negative 1 up to 1, but now we just have positive x values on this. So our sine inverse function only is going to spit out these angles. So we can't get anything over here. That's kind of annoying. Oh well. Let's take a look at cosine inverse. So this is our cosine function graphed between negative pi and pi again. And you'll notice he drew some horizontal line stuff and you get all screwy, right? So what we're going to do is we're going to restrict our cosine function to just this right half. We're going in between 0 and pi. So again, you'll notice you get this nice boundary from negative 1 up to 1. We get all those y values here, but we don't have any problem with the horizontal line test if we just restrict to this piece. So what we're going to do is reflect this one. So I'll draw my line. Something like that. We're going to reflect it across this line. So we get this graph. So again, here's that line that we reflected across. And hopefully you can see that that red graph, I probably should have used a different line, or a different color for my line. I'll do black. You can see that that red graph is reflected really nicely across this line. So there's your cosine inverse function. If we go back to this one, let's plot some points on here and just kind of label coordinates. This one right here. Oh my gosh, get rid of my ruler. Keeps wanting to draw a straight line. This is pi comma negative 1. This is 0 comma 1. And this is pi over 2, 0. All of these points are going to get reflected. So this one here, 0, 1, gets reflected to 1 comma 0. Pi over 2, 0 gets reflected over here to be 0 pi over 2. And pi negative 1 gets reflected over here to be negative 1 pi. So those are our 3 points that we care about right here, here, and here on the cosine inverse function. Again, as a quick summary, we can say these two things are the same statement. Since cosine is not 1-to-1, we restricted the domain. Oops, I wrote sine here on accident. That should be cosine. Of the cosine function to 0 pi before we find an inverse function. And that means that the cosine inverse is only going to give us angles between 0 and pi. So again, our range here is 0 to pi. Our domain is still negative 1 to 1. We can get all those ratios. Let me go ahead and draw another unit circle. And we will see what kind of angles this thing is going to give us. I'll go relatively slowly so it's not a terrible circle, but it's still not great. Oh well, don't care. Angles between 0 and pi are going to be these angles. So we're only getting these first 2 quadrants instead of the first and the fourth quadrant when we get those cosine inverse. We'll spit out angles up here on the top. So we miss these angles down here on the bottom of our unit circle. Here's our tangent function. If we want to find the graph of the inverse function, we're going to need to do the same thing. Again, horizontal line test screws us up. We go through a whole bunch of graphs if we do that, or a whole bunch of points on the graph if we do that. So what we're going to do is we're just going to look at this middle piece, which seems reasonable enough. We'll just grab one of these little bits between the asymptotes. So if we just focus on this one, again, we can go ahead and grab a couple points on here if you want. There's this point right here at pi over 4, 1. Actually, you know what? I'm going to do this a little later. But we'll reflect this. Notice we have some vertical asymptotes. If we reflect those, they're going to become horizontal asymptotes. So now I've got these points at 0, 0. You can see really easily that that one stays the same. If you flip the coordinates around, it's the exact same thing. This one here is at pi over 4, comma 1, because that's sine of pi over 4 over cosine of pi over 4. And remember, those are the same thing. And then the same thing at negative pi over 4, we get negative 1. So if we flip those points, we get some points right here that are going to be 1 pi over 4 and negative 1 negative pi over 4. It's kind of hard to write, but oh well. So this is what we've got. I flipped the kind of scales here so you can see the pi stuff. So what we'll notice is that we have horizontal asymptotes. So that's kind of new for us. Let me write that. Horizontal asymptotes. We've got 2 of them. One of them is at pi over 2. Well, maybe I'll do the negative pi over 2 first. And pi over 2. Because there were vertical asymptotes on our tangent function, when they get reflected, they become horizontal asymptotes. This thing goes to the origin, 0, 0. We've got this point here, 1 comma pi over 4. We've got this point here, negative 1, negative pi over 4. And that gives us our tan inverse function. Same kinds of properties. Oh, I did it again. I must have copied pasted and forgot to change cosine or sine to tangent. I'll change that in the notes before I put them up. These two statements are the same. Since tangent theta is not 1 to 1, we still had to restrict the domain, but this time we restrict it to open negative pi over 2 to pi over 2. Since we had asymptotes, we don't get to use closed parentheses around here, which means we actually skip those angles, which makes sense. Our tangent function isn't even defined there, so of course we're going to skip them. That means that we're only going to be giving us angles between negative pi over 2 and pi over 2. The vertical asymptotes on the tangent function become horizontal asymptotes on the inverse tangent function. And notice that the domain now is actually negative infinity to infinity, because that was the range of our tangent function, because our tangent function went down on that vertical asymptote and up on that other vertical asymptote. We got all the y values. That becomes the domain for our tangent function. And then the range is everything in between negative pi over 2 and pi over 2. And then we also have those horizontal asymptotes. What that means is on the unit circle, if we take a look at what kind of angles this thing is going to spit out, we're going to be looking at angles between negative pi over 2 and positive pi over 2. But maybe I'll put like a dotted line here, kind of. It's hard to see. But we don't actually get those angles. So it's just everything in the first and fourth quadrant without that vertical axis. And those are the only 3 that we talk about too much. Well, where are the rest? What about the other ones? If you take a look on your calculator, you'll notice you only have sine inverse, cosine inverse, and tangent inverse, most likely. There's not a cosecant inverse defined, or a secant inverse defined, or a cotangent inverse defined. And so the question is, well, what if I need those? How do we deal with that? This, I don't think it gets covered too much in the text, but let me just show you really quickly. It's actually not hard at all. For cosecant inverse, we'll just say y equals cosecant inverse of x. That's the same as x equals cosecant y. Flip the input and output and you get the function. Well, we know what cosecant is. Cosecant is 1 over sine. So really, x equals 1 over sine y. Well, that means that sine y is 1 over x, if we just look at the reciprocals, or you could multiply sine y on both sides and divide by x. And so we can solve for y by using the inverse sine function. So cosecant inverse is really the sine inverse of 1 over x. So we use this reciprocal thing because sine and cosecant are linked, but we're doing it on the input instead. Similarly, you could say x equals, maybe I'll use a different color for this one. We'll say x equals secant y. That's the same statement that we had. We just switched the inputs and outputs. So that means x is 1 over cosine y. So that means cosine y is 1 over x. And then you can see again, we'll just use the inverse function for cosine. And we have this reciprocal composed on the inside. And you can see how this one's going to go. Y is going to be tangent inverse of 1 over x. So if you want cotangent inverse, if you want secant inverse, if you want cosecant inverse, you can just write those in terms of sine inverse, cosine inverse, and tangent inverse. So that way, if you really need to do something with that on your calculator, grab these things here. That's kind of neat, I think. So now what we want to do is talk about composition. And there's kind of two cases here. There's going to be a real easy case where you have a trig function and its own inverse composed. And the only thing that we have to be careful about is domain, because we know that the inverse functions are only going to spit out certain types of angles. But outside of that, this is going to be pretty easy, because we know that a function and its inverse undo each other in general. Then we're going to have like a not so simple case where you have a trig function and an inverse function composed, but they're not the same. So instead of like a sine function and a sine inverse function, maybe it's a sine function and a cosine inverse function composed. And we'll have to kind of play around with that and see what we have to do. Try to remember that each of these functions are really certain things. Inverse functions are really angles, and regular trig functions are ratios of side lengths or coordinates. So let's just take a look at this real quick. Cosine of cosine inverse of half. So maybe we'll just notice that this is just some angle theta. And it's an angle such that cosine theta equals half. That's how we're defining this thing. Whatever this angle is, it's the angle where the cosine of that angle is going to give you half. So what is cosine of that angle? Well, we just said it right here. Cosine of that angle is supposed to be half. Again, function and its trig and its inverse are undoing each other. So this thing is really just half. That's pretty easy, right? This, we have to be a little bit careful about. This is a ratio of side lengths. It's some ratio or coordinate. Maybe I'll say it's the y-coordinate on the unit circle. We're good at unit circle stuff now, right? So this is the y-coordinate, where we want to know what's the sine inverse of that. Well, sine inverse of that is going to be some angle that gives us this y-coordinate. So what we have is that this is a y-coordinate such that sine inverse of y equals 5 pi over 3. But that's not going to make any sense, because sine inverse of y can't be 5 pi over 3. Pause the video for a second and try and figure out why that's true. How come sine inverse of y can't be 5 pi over 3? All right, I just skipped back to the summary of inverse sine, and hopefully we can see. Sine inverse of y can't be 5 pi over 3 because the range is only angles between negative pi over 2 and pi over 2, sorry. And 5 pi over 3 is not in here. So that's a problem. I'm going to get rid of that. I'm going to skip back down to the end, and I'll just write it there. So here we go. Our angle 5 pi over 3 is right here. It's pi over 3, right around there, less than 2 pi. But what we really are only working at is like we have to spit out the negative versions of those angles, right? Because we're okay to be in this quadrant, but let me draw it this way. We're going around like that. What we want to do is do this. So we'll say, okay, this is the same angle as negative pi over 3. And our sine inverse can spit that out. Now, that's okay because sine of 5 pi over 3 and sine of negative pi over 3 are the same thing. Because those angles are coterminal, they're going to give us the same y value on the unit circle, or they'll give us the same ratio of side lengths if we draw a little triangle there, no matter what the radius of our circle is. And we can kind of get the same value for sine. So whatever this y value is, that's the same, let me write it here. That's the same as saying we need to do sine inverse of sine of negative pi over 3. So that's going to be negative pi over 3. So really, instead of just jumping into saying, oh, it's going to be whatever this value is, Find the coterminal angle that's going to actually be the same thing. Every now and then you might get something that's in a completely different quadrant than what we give. But then what you could do is say if you had an angle like this, the y value here and the y value here are the same. So find the other angle that gives you that same value of sine. Maybe it's not coterminal. Maybe it's something like that. So that's really the only thing that we have to worry about. And now we've got this last one, tan of tan inverse negative 10. Our tan inverse function can take in any values. Remember, we had those horizontal asymptotes, so the domain of this was negative infinity to infinity. Our tan function can spit out any value. So this is some angle where that angle is the angle such that tan of theta equals negative 10. Well, we're asking for tan of that thing. So this is negative 10. So these are kind of the, quote, easy cases. The only hard one, I think, is this middle one here, where we have to worry about the domain restriction and that kind of thing. So let me kind of cut this off like that. So here, the main key is if the angle isn't in the restricted domain of the sine function, well, let me skip down here, then we need to find a different angle that is in that domain that gives us the same function value for sine. And this is the same thing for cosine. So we found out that sine of 5 pi over 3 and sine of negative pi over 3 were the same thing. And we also know that negative pi over 3 is in that restricted domain. So that's the value that we can use. That's kind of a weird thing. Here's some harder composition examples that we can take a look at. And for these, we're going to have to just continually draw some stuff and figure out what's going on. This doesn't get too hard once we figure out what's happening. So the main thing to notice is that, again, this tan inverse is an angle, theta. And it's an angle such that tan of theta is 3/5. So what we want to do is figure out what the cosine of that is. And that's hard for us to do because now we don't have, the statement cosine of theta is that. Over here, that was really easy because we said, if tan theta is negative 12, we want to find tangent theta. So we've already got it. We're done. Hooray. What we have, maybe make that 3 a bit more clear. What we have is the ability, though, to draw a triangle. Here's my right triangle. Here's my angle theta. And if I know that tangent of theta is 3/5, I know that the opposite over the adjacent side is 3/5. And now I can just say, what value of cosine of theta am I looking for? Well, cosine of theta is the adjacent leg over the hypotenuse. We just need to figure out what the hypotenuse is. The hypotenuse is going to be the square root of 5 squared, that's 25, plus 3 squared, that's 9. 25 plus 9 is 34. And that doesn't really simplify at all, so we'll just leave it as 34. So what we've got is that cosine of theta is 5 over root 34. It's our adjacent side over hypotenuse. So we'll take this statement that we get and we'll just turn it into a picture of a right angle triangle that we can then, should make sure that's a right angle, that we can then use to find the value of cosine of that angle. So do this second one. See if you can figure that one out. Figure out what your angle is going to kind of be. It might not be one that we know, but we know the cosine of that angle, and then go ahead and draw a picture and see if you can figure things out. If you haven't paused the video yet, do it. Seriously, do it though. Okay, hopefully you paused the video and now you're back. So for this is an angle, theta, and what we know about that angle is that the cosine of that angle is root 5 over 7. So bang, we've got a right angle triangle, and we know two sides of it. The two sides that we know are the adjacent side and the hypotenuse. The hypotenuse is 7. I'll draw my angle right here. The hypotenuse is 7. The adjacent side is root 5. So we can figure out this side. Oh, I should have done that while I was telling you to pause the video. This is going to be the square root of 7 squared minus root 5 squared. So that's 49 minus 5. So that's 44. That's really the square root of 4 times 11. So I'll say that's 2 root 11. So we want to find sine of this thing. Well, sine of our angle now is going to be the opposite side over the hypotenuse. So it's 2 root 11 over 7. So what we've got here is, in general, we can say cosine of tan inverse 3/5 is really cosine of that angle. So we'll say it's 5 over root 34. And sine of cosine inverse root 5 over 7 is really sine of this angle that we've drawn, and that was 2 root 11 over 7. So again, use the information about the angle cosine inverse of root 5 over 7 to tell you some things about the sides of a right triangle. And then you can go ahead and fill in the rest. That's kind of neat, right? Here's some even harder ones. Try this. What I might do is rewrite this real quick and say this is the same thing as sine of cosine inverse x over 1. X is the same thing as x over 1. Now, this looks a lot like this second problem that we did. Sine of cosine inverse of something over something. Build your triangle and see what you get. Same thing here. This is secant of tan inverse x over 1, 2 side lengths. I'm going to pause this. I'm going to let you try and think about how this goes. Or I'll let you pause it, sorry. And let you think about how this goes. And then when we come back, we'll have some triangles and stuff. All right, so here we go. So I started off and I said, hey, this thing right here, cosine inverse of x over 1, that's an angle. It's an angle where the cosine of that angle is x over 1. So I've drawn that. The adjacent side is x. The hypotenuse is 1. I use the Pythagorean theorem to fill in this third side length. Square root of the hypotenuse squared minus this other side length squared. So 1 minus x squared. So now if I want to find sine, it's just going to be opposite over hypotenuse. So this is the square root of 1 minus x squared over 1, or square root of 1 minus x squared. Similarly, this tan inverse of x over 1 is really an angle where tangent is x over 1. So the opposite side is x, the adjacent side is 1. And now if I want to find the secant of that, that's the reciprocal of cosine. Cosine is the adjacent leg over the hypotenuse, but now we're going to do hypotenuse over adjacent because secant is the reciprocal. So 1 plus x squared under our square root over 1, or square root of 1 plus x squared. Hopefully that makes some sense. Hopefully we can compose some of these things with each other and get some of these kind of weird expression values. They've got some weird square roots in there because of the Pythagorean theorem, but that's not too surprising. Anyways, that's all I've got on this. Jump into the text, see if you can find some other nice examples to look through. Try those practice problems, and hopefully this goes pretty well for you. Let me know if you have any questions.